Us now. Here is our notes. We discussed till nuclear fission and fusion, right?
Yes, sir. Sir, will
Mm-hmm.
you give us the MC, like the mark scheme?
Mark scheme I will give later. That will be better
Can you
because
just give us the MCQ part, not the structure part?
okay, I can
Since
give
I
no
finished it,
problem.
I need to know which I'm doing wrong or
Yes,
correct.
yes, yes. I will give you no problem. Now, can you tell me the difference between nuclear fission and nuclear fusion?
Nuclear fission is the breakdown of lighter nuclei. It is done in uh, factories, or what do you call it? Factories,
Again,
right, sir?
what again, please?
And nuclear fission is the breaking down of nuclei of an atom into two different nuclei
Yeah, you
and
add their heavier nuclei is breaking down to
into
lighter
lighter
nuclei.
nuclei.
Yeah,
And nuclear fusion is the making of two lighter nuclei into a heavier nuclei,
yeah,
which is done in the sun.
yes, yes, very good. So this one is the very basic idea about nuclear fission and fusion, and other things uh, are extra, like the information you told. Normally about nuclear fission and fusion, MCQ questions are coming from this knowledge only. So far we got, and we have some more information today. In this part we discussed last class. Here we have some, you know about the use of nuclide notation, right? That if it is uranium 92 235, then one neutron is coming here. So we are having 236 here, right? So 236. Then they will test you sometimes that are you aware of this atomic numbers adding, like it is 92, so 36 and 56 will be 92. Okay, uh, does it match? 92, 36 and 56, it is 92, right? So they will test you that is it matching or not matching. If they are giving you here 35, then it's not matching, so this option will not be correct. Then here 236, we are having here 92, 141, and 3 neutrons. So it's coming 236. Do you understand what I'm saying? The
Yes.
the mass number
How
and the atomic number. Does it match? Sometimes they are giving you questions like if they are giving you structured questions, this place will be blank, right? The other information will be given, like 140, 156 will be given, 92 will be given, 36 will not be given, 310 n will be given. So 36 you have to find. Can you do it? Is it possible to do? Hello?
So I don't understand what you're trying to say.
Okay,
can you please repeat?
I'm repeating, no problem. Look, here we have the nuclide notation of uranium, right? Uranium 92 236, and here we got uranium 92 235. So how we got this 236? Can you tell me now?
By adding one neutron.
Yeah, by adding one neutron, and neutron has mass of 1, right? So
Yes.
that one will be added with the mass number 235. It's not added with the 92. Is it clear?
Yes,
Hello?
sir.
Okay,
Yes,
so
sir.
1 and 235, it's making 236. Now this 236 is uh, is divided into three parts. One we got 92, another one we got 141, another one we got 3. So here we have 3 neutrons. Hello Adnan.
Assalamu alaikum, sir.
Walaikum salam. Thank you for joining. Okay, now
Welcome.
look, 3 neutrons means it has mass number 3, right? Aisha.
Yes, sir.
So this 3, it is mass number, 92 is mass number, then 141 mass number. So does it match with 236 if you add them together? Is it coming 236? Hello?
Yes, sir.
Okay. Here we have 3. 3 ones are 3, yeah, mass number. So we have 236. Now we have here 92. 92 will be divided into 2 parts. Neutron, it does not have any atomic number, right? Or it does not have any protons. So atomic number is related to the proton numbers. So 92 is divided into 2 parts, 56 and 36. It's making 92. Is it clear?
Yes.
Yes, sir.
So if in question they will give you everything, only they will not give you this 36. Okay, then you can find it.
It's just simple minus and plus,
Yeah,
right?
simply you will minus 92 minus 56. It will come 36. Is it possible?
Okay.
Yes, sir.
Yeah, that one I was saying. So here we got nuclear fission, and here after that we got some more information in our discussion before. We also brought this idea that controlled and uncontrolled nuclear fission. So when it is uh, happening, the nuclear fission, we are getting 3 neutrons, right? Here you saw that we got here 3 neutrons. These 3 neutrons will hit uh, more 3 uranium nucleus. Do you understand? Then what will happen?
Yes.
This process will
More.
continue. Yeah, this process will continue. And if this process is continued this way, then there will be uncontrolled chain reaction. As from one reaction, we started one reaction only, and from that we got again three reactions. You see, 3 neutrons means those 3 will hit another 3 uraniums, and after that what will happen? Again we will get 9 neutrons, right? So those 9 will hit more 9 uranium nucleus. This way this process will continue. This one is called uncontrolled chain reaction. And if we have that uncontrolled chain reaction, then it's happening in the atomic bomb. Yeah. That one happened in Hiroshima, Nagasaki. If uncontrolled, as in the case of the so-called atomic bomb, it can lead to an explosion which causes massive destruction. Right? Is it clear? Now, how to make it control, we are going to discuss. We are going to discuss that one. In nuclear reactor, we have controlled chain reaction. A chain reaction can provide power. Power means electrical power, electricity, electrical energy, power for society's benefit. We are going to discuss that one when it will be controlled. You see, here we got uncontrolled chain reaction here. Look, uranium, then we are getting here krypton, barium, 3 neutrons. They are hitting more uraniums. Then we are getting, always it's not happening that we are getting barium and krypton always the same way. Sometimes we are getting cesium, rubium, then xenon, we are getting strontium, we are getting this way we are getting different types of nuclei we are getting. So got it? We are getting also indium. Here we got iodine. Is it clear, everyone? Hello?
Yes, sir.
Okay, so if you are more interested to see, we have some links here. We have some links here. If you have some time, you can manage some time. Here we are having the whole process, how the nuclear, this video, the first video, you will see how there is the control chain reaction working in power station, nuclear power plant. There will be control rod, and there will be moderator, and those will control the nuclear chain reaction. Uncontrolled one will be controlled. So, and another video, you will see nuclear fission details. In details, you will get lots of things over there. So here we have nuclear reactor. How does it work? There will be more discussion on, you see, here we have fuel rods, moderator, control rods, how they are working. And the last class, I told you that nuclear power station is similar to thermal power station. And here are the steps. First, we are getting the thermal energy over here. Then this thermal energy, we are producing steam. Steam turbine is over there. Then steam is, turning the generator, is working on the generator, and we are getting the electrical energy. So only the first part is different. In the conventional power stations, which are run by the fuel, we are getting the fossil fuels, coal, gas, and petroleum. Those are using those fuels, and we are burning them to get heat energy. In nuclear power station, we are getting nuclear reaction to get the heat energy. Okay, that heat energy is used to do the other steps. Okay, you got the similarity of nuclear power stations and conventional thermal power stations. Is it clear, everyone?
Yes, sir.
Yes, and this one is the simple, diagram, schematic diagram or block diagram, you can say. So here you got the idea. Now we are starting from here again, no problem. Here, Adnan, you please read from here, a nuclear reactor. Adnan is there? Hello, Adnan. Yes, Adnan is there. His microphone is not working. So, Moshe, you read. Moshe,
Yes, sir. Yes, sir.
yeah, read. You read from here. A nuclear reactor.
Okay, sir. A nuclear reactor produces and controls the release of energy from splitting the atoms of uranium. Uranium-fueled nuclear power is a clean and efficient way of boiling water to make steam, which drives turbine generators. Except for the reactor itself, a nuclear power station works like most coal and gas-fired power stations.
Okay, wait. We got here one very important thing, that nuclear power or nuclear energy we are getting. Uh, the electricity you are producing from nuclear power station, that one is clean, clean and efficient. So why is clean? Because we are not getting any smoke over there, any dust over there. But in fossil fuels, we are getting so. That's why it is clean. And why it is efficient? It is efficient because in nuclear reaction, we are getting so much energy, so much heat energy, too much heat energy in comparison to the one we are getting from fossil fuels. Is it clear why it is efficient and clean? Hello, are you clear
Yes,
why
sir.
it's clean and efficient? You might have this idea before also when you went through the topic, the one you did before in thermal physics, the first topic we got, where we discussed, maybe Shamim sir discussed it, right? In class 8, you got it, isn't it?
Yes, sir.
There you got like different kinds of energy, renewable energy, non-renewable energy, right? And what are the advantages of renewable energy, disadvantages of renewable energy, those things you got there, right? So here this term came, clean and efficient. So this is the advantage of nuclear power station, that it is clean and efficient. And there are some disadvantages also, like they are very expensive, there are some risks, and if you can maintain it properly, it is a good one, nuclear power station. Okay, now this one, already we have the idea about the block diagram. Now continue here. Yeah, Moshi, continue here.
Yes, sir.
Several hundred, yeah.
Several hundred fuel assemblies containing thousands of small pellets of ceramic uranium oxide fuel make up the
Mhm.
core of reactor. For a reactor with an output of 1000 megawatts MW, the core would contain about 75 tons of enriched uranium. In the reactor core, the uranium-235 isotope fissions or splits, producing a lot of heat and continuous process called a chain reaction.
Okay, okay. Wait. Here we got some of the terms. I just give you some idea. They use here enriched uranium and pellets. You understand, right? They are using the pellets of ceramic uranium oxide. That means not only completely uranium. They are giving some mixture, right? Ceramic uranium oxide. We are having this. So oxide of uranium we are getting as fuel make up the core of the reactor. Huh? And enriched uranium means we actually for um, a power station we need uranium 235. But in nature we don't have enough 235. We normally we have 238. You see what is enriched uranium, we have some idea here. I'm going there. Can Ziba, you read what is enriched uranium? Just to have a idea here.
Enriched uranium is a type of uranium in which the percent composition of uranium-235 has been increased through the process of isotope separation. Naturally occurring uranium is composed of three major isotopes: uranium-238, uranium-235, and uranium-234.
Okay.
235 uranium is the only nuclide existing in nature that is fissile with thermal neutrons.
Hmm. That means
Enri-
the neutrons we are giving over there for nuclear reaction is working better with 235 uranium. Okay, that's why we are increasing its ratio. There are some process, those we do not need to discuss here how to enrich it, but at least you got the idea that what is enriched uranium, where there will be greater ratio of uranium 235. That is called enriched uranium. Okay, clear? And sometimes in newspaper we get this idea that that Iran is enriching their uranium, then North Korea is enriching uh, their uranium.
Can you explain enriched uranium again?
Sorry.
Please? Can you explain Enriched uranium again, please.
Again, please.
Enriched uranium.
Again, please.
Enriched uranium. Can you
Okay.
explain again?
Okay. Enriched uranium means the uranium we are getting in nature. That is mostly, we are getting 238, uranium 238, uranium 234, and uranium 235 also we get in nature. But we need for nuclear chain reaction, we need uranium 235 because it's working better for the chain reaction process. So the process how we are increasing the number of uranium 235 by isotope separation, this process is called uh, uranium enrichment, and the uranium we get in this process, that is called enriched uranium. Is it clear now?
Yes, sir. Thank you.
Okay, you are welcome. Then we are getting a very important thing here, a moderator. We are talking about this one, that how we are making the uncontrolled chain reaction to controlled chain reaction. So here we have these two things, moderator and control rods. These are helping us mostly to do that. So can you continue here, Aisha?
Okay. A moderator slows the fast neutrons down and makes fission possible. Control rods help in adjusting neutron flux, which in turn affects power output. The basic function of these rods is to absorb neutrons. While starting a reactor, control rods are pulled out so that power output increases and reach the desired level.
Okay, wait here. So here we got moderator. Moderator, it slows down the neutrons. So here the neutrons we are giving, that neutrons require to have level, certain level of kinetic energy. If it has too much kinetic energy, is too faster, then it does not work. The fission is not working properly because the uranium has to absorb this in the nucleus. It has to absorb this the neutrons, the fast moving neutrons. If the neutron is too fast, then it cannot absorb it. Uh, and you see here, for the time being, we have this unstable nucleus. That means uh, stays the neutron, it works over there for a certain time, like a little bit time it has to stay inside the nucleus, so that the the breakdown process can work properly. Okay, if it is too fast and it's just touching and going, then it cannot be happened. So we have to make it certain level of kinetic energy, the required one for the fission, make the fission possible. We use this moderator. Is it clear to you? And this moderator is made from graphite, and graphite, is a little bit elastic type of things, right? So it will slow down the neutrons. Do you understand what I'm saying, everyone? Hello, hello.
Yes, sir.
Yes,
Yes,
sir.
sir. So graphite we are using as moderator. You just remember this one. We are using graphite. Graphite, right? The carbon is made from carbon, and we have here control rods. Control rods, as already you read, you understood that it's controlling the number of neutrons coming. It can increase the supply of neutrons, and it can also decrease the supply of neutrons. So if the supply of neutrons more, then there will be more reaction. If the supply of neutrons less, and reaction will be less. So it depends. When we need more, reaction, we need more power in the nuclear power station. That time we, you see here, we have the control rod here. Here, control rod, sodium metal. So this control rod, you move up and down. Move up and down. Here you see red color control rods. So it's controlling the number of neutrons coming, so that we can increase or decrease the amount of reaction. And if your power station has already lots of energy production stored, uh, so that time we are controlling the reaction more, then we need less electricity now, right? That's why. If we need more electricity or we need more energy, more heat energy, that time we are taking it out, we are taking it up. Okay, then we have more reactions. Is it clear about moderator and control rods, everyone?
Yes, sir.
Very good, very good. Thank you. Now, Ziba, you continue the last part, the heat.
The heat released by fission in nuclear reactors must be captured and transferred for use in electricity generation. To this end, reactors use coolants that remove heat from the core where the fuel is processed,
Processed. Yeah.
and carry it to the electrical generators.
Mhm.
Coolants also serve to maintain manageable pressures within the core.
Yes. So coolants, yeah, we are actually using the uh, heavy water. It's called D2O, deuterium. Deuterium, one of the isotopes of hydrogen. Hmm?
Yes.
So that one,
Yes.
if we are using to make water with that hydrogen, that is D2O. Normally, the water we are getting, that is H2O. So that
O
one,
will be denser.
yeah, that one is called heavy water, and that heavy water is used here in the nuclear power station as coolant. Okay, so this coolant is actually
E2O,
taking, again, please.
T2O ওইটা
D,
কোথায় ইউজ হয়?
D2O. We are talking about D2O.
T2O ওইটা কোথায় ইউজ হয়?
Heavy water. Here we are using
D না T.
এটা
T2O.
শুধু
Okay,
ফিজিক্সেই
okay,
সম্ভব।
okay, okay. I understand now. I understood your question now. T2O. That one, actually, I don't have any idea now about T2O where it is used, or maybe it is not used anywhere. Okay, it is there. Uh, it's in water. We have little amount of D2 also, ratio, like in the one you got before, that uranium in nature we have the ratio uranium 238, 235, and 234 mostly. Uh, Similarly, we have in nature D2O, but I never heard about T2O. Okay, so today I will check it. Is there anything T2O? Very good. Thank you so much, Adnan, for your question, which will help me to get some more ideas, inshallah. Okay, now uh, the same way, the similar way, the way we got uranium 235 for power station, we are making it, by enriching. The similar way, we are also producing D2O for nuclear power station, to use them in the nuclear power station. So why we are using them? Because water has high specific heat capacity. It can absorb lots of heat, right? Do you know that? Other than uh, you know other than most of the liquids, water has greater specific heat capacity, and in between normal water and heavy water has even more. That's why they are used here uh, to get the heat from the nuclear reactor, to use them to make vapor, huh? To make steam, so that it can absorb more heat. There will be less heat loss. Do you understand? Hello?
স্যার আরেকবার একটু বুঝাবেন?
একবার
That one, specific heat capacity one, I think you need to understand, right? Is it?
Yes sir, please.
Okay, yeah. Specific heat capacity, can you recall that in your thermal physics you got this idea, the substance which can absorb more heat. Like you are taking 1 liter of water and 1 liter of petrol. Okay, so 1 liter of water, uh, you are giving the same amount of heat from your stove for 10 minutes. You will see the temperature you got for the petrol, the temperature you got for water. You'll see after 10 minutes the temperature of water will be less and the temperature of petrol will be more. You'll see that petrol started boiling, huh? Started boiling, but water is still not. That means water has more capacity to absorb it. It will become vapor, or it will reach to its boiling point after this petrol. Okay, so it can absorb more and more heat. Maybe after 15 minutes it will be boiling. Do you understand now how we can compare specific heat capacity?
Yes sir.
Okay, so which one has more specific heat capacity? That one is absorbing more energy, right? This idea you
Yes sir.
got. So in between heavy water and normal water, heavy water has more specific heat capacity. That means it can absorb,
B2O.
it can take more heat energy from the reactor. Okay, so this one will be better coolant. Okay, and it can absorb more heat, and this, if it can absorb more heat, it can transfer more heat here, right? From the reactor. Is it clear now? Hello?
Yes, sir.
yes
So
sir
if it can transfer more heat here, that means normally what happens in the nuclear reactions, we are getting around 6,000 degrees Celsius, right? The temperature. So 3,000 to 6,000 degrees Celsius. So if it is 6,000 degrees Celsius, that means it's getting more heat energy, too much heat energy. So if that heat energy we can absorb more, we can get more speedy steam, right? More the steam with more kinetic energy, right? That one can turn the turbine more. You can turn a bigger turbine then, and you can run a bigger generator then, right? Clear? Hello?
yes sir
Yes
So
sir.
so then you will get more electrical energy. You will get enough efficient, your process will be very much efficient. So this way our coolant is working. Okay, now is it clear how the coolant is working? Hello?
yep
Hello?
Yes,
Okay,
sir.
so
Yeah.
we will continue our next class after 5 minutes. Okay, inshallah, the same link, huh? Okay,
Allah
Allah
Okay
Hafiz.
sir.